Okay, we've looked over error intervals, we've looked over upper and lower bounds, so we're now going to look at combining this all together with some exam-style questions. Before we get into them though, I think it's useful to consider the basic idea of what we're trying to do. Here we've got two numbers which have been rounded. So we've got 50, which has been rounded to one significant figure, and 10, which has been rounded to the nearest integer, so that's to the nearest 1. The first significant figure is the 5, so that's been rounded to the nearest 10. So if we do the same thing we did last week of halving and then adding and subtracting to get our upper lower bounds, so 10 divided by 2 is 5, and 1 divided by 2 is 0.5. And then we get the, I suppose, limits are going to be between 45 and 55 for that one, and between 9.5 and 10.5. Okay, so that's our error interval. What about this question though? What is the upper and the lower bound for a plus b? Now, what people do wrong here is the following. They add the 50 and the 10 that they can see at the top of the question. They get 60, and then they round it, and then they say, okay, well that's between 55 and 65, and that is not how we want to approach this. We want to do our upper bounds first and then do the sum, or lower bounds first, depending what we want. Now if we want to get the largest possible value for a plus b, and we can choose anywhere between 45 and 55 for a, and anywhere between 9.5 and 10.5 for b, then to get the biggest answer we want to choose the biggest answer. So we want to choose a large value of a and a large value of b. That'll give us, let's do this a bit better, 55 plus 10.5 for our upper bound is 65.5, and our lower bound, we would take the lower value of a and the lower value of b. That would give us 45 plus 9.5, which is 54.5. You can't get a higher value than 65.5. You can't get a lower value than 54.5 using that sum. What about if you're doing the same with a minus b? A similar mistake here is for people to say, well, I'm finding the upper bound, so I need to take the upper bounds of both the numbers, and they'll do 55, take away 10.5, and they'll get themselves to 44.5. But you can actually do better than that if you take the lower bound of b. 55 minus 9.5 would give you 45.5. So just because you're finding an upper bound doesn't mean that you always take the upper bound of everything in the sum. You have to think about, well, what's the biggest answer I could get out of this? And you get the biggest answer for a subtraction when you start with a large number and take away a small number. If we wanted to find the lower bound of this sum, we'd reverse the process. We'd find the smallest value of a and the largest value of b. And we do 45, take away 10.5, we get our lower bound is 34.5. Now you could be asked to put this as an error interval. If you were going to do something like that, we'd have 54.5 less than equal to a plus b less than 65.5, and for the second one we'd have 34.5 less than equal to a minus b less than 45.5. So let's consider the same numbers. Again, we've got a is somewhere between 45 and 55. We've got b is somewhere between 10.5 and 9.5. And what about if we had multiplications or divisions? So if we wanted to find the upper bound for a multiplication, what would you use? Would you use the largest values, the smallest values? I think you'd use the largest values. We'd want to use the upper bound of a and times it by the upper bound of b. So our upper bound for the multiplication would be 55 lots of 10.5 would be 577.5, and our lower bound would be the lower bounds multiplied by each other. That would be 45 times 9.5, which would give us 427.5, and we could say our error interval there is 427.5 less than equal to a times b less than 577.5. What about a divided by b? Well, we could, I guess, if we want to get the largest value for a division, we want to divide by a small number. We want that number to fit into the first number the most amount of times. So we want a to be large and we want b to be small this time, just like we did with subtraction. So our upper bound would be 55 divided by 9.5, which is 5.79 or thereabouts. For our lower bound, we'd want to take a small value of a and divide it by a large value of b. That would give us 45 divided by 10.5, which is 4.33. Have a mess around with this maybe, because maybe division isn't that intuitive, but these will give us our biggest and our smallest amounts. So we can summarize this in this overly complicated table. I've done this little small version of it here that I'm going to keep in the bottom right of the screen. But yeah, you need to make sure that if you're told to maximize a multiplication, you know exactly what you have to do. Okay, let's look at some applications here. We're rounding to one decimal place, which means we rounded to the nearest 0.1, which means if we halve it, 0.05 is what we need to add and take away. So our error intervals for these two firefighters is 195.55 up to 195.65 and 170.35 up to 170.45. Not a lot of range in them, but there we go. We want to find the maximum possible difference in their heights. So if this is our A and this is our B, difference is going to be the A minus B. If we want to maximize this, that means we want to find the upper bound of that. We know that we need to do, let's look at our list here, the maximum value of A take away the minimum value of B. So we want to do 195.65 take away 170.35, and that would give us the biggest difference in their heights would be 25.3 centimeters. There you go, there's an application of using that little table. Let's look at a similar one here. Packet of crisps weighs 34 grams to the nearest gram, so that's to the nearest 1. If we divide that by 2, we get a half. So the weight is somewhere between 34.5 and 33.5. Pack of crisps contains 10 packets. That's not been rounded at all. So you don't need to say that's between 10.5 and 9.5 or anything. That hasn't been rounded. What's the least and the greatest weights of the multipack? So that is a multiplication because we're multiplying the weight by the amount. We're going to get the least and the greatest this time, so let's do the greatest first. For the greatest one, we want to do upper bounds times upper bounds, so we're going to do 34.5 times 10. That's 345 grams. And for the least, we want to do the lower bounds multiplied by each other. So that's 33.5 times 10. That's 335 grams. Fair enough. Let's increase the difficulty though and look at some slightly more in-depth questions. We've got a rectangular garden with a length of 40 and a width of 25, both rounded to the nearest meter. This means we've rounded to the nearest 1. So if we halve that, 0.5 is what we need to add and take away. That means that our length is going to be between 40.5 and 39.5. That means our width is going to be between 24.5 and 25.5. Okay, so we've got our bounds. We've also got a different garden which has an area which has been rounded. We're going to come back to that in a second. Mira thinks she's got a bigger garden than Luke, so what we need to do is find the bounds of the areas of both gardens. Now for finding the area of Luke's garden, we're going to do length times width. So if we want to get the upper bound for that, we need to do the upper value of L times the upper value of B. So that's going to be 40.5 times 25.5, and the lower bound for Luke's garden is going to be the lower bound, so 39.5 times 24.5. That gives us values either side of 1,000, and we could summarize that the area for Luke's garden is somewhere between 1,032.75 and 967.75 meters squared. What about Mira though? See, Mira is different because it doesn't give you length and width and say they've both been rounded. Mira gives you the area and says that's been rounded. So this is this rare case where you take the final answer and that's what you add subtract to. This has been rounded to the nearest 10. So if we halve it, it's 5 that we need to add and subtract from that. So Mira's garden is just between 975 and 965. Now, we need to answer the question, Mira thinks her garden has a bigger area, and that could be true. It could be true if she had a 975 and Luke had a 967.75, that's fine. But it's not definitely true, because if Mira's garden was 965 and Luke's garden was 1032.5, then he would have the bigger garden. So our summary here is going to be something like, she could be right, and we'd have to actually mention the fact that we found that 975 and that's bigger than 967.75, but she also could be wrong. And in that case, I'm struggling to write for a second. There we go. And that case would be, well, she could have a 965 and that's way less than Luke's potential upper bound. So make sure that you do all the calculations to start with. We found our bounds, then we found our upper and lower bounds for the areas, and then we made our statement. Don't go straight into the statement, you won't get the marks for it. We're going to look at a few more questions here, but I think now I'd like you to have a go first. So I'm going to assume you're pausing now. And let's come back to it. As always, you want to figure out the bounds of the things that are in the question first. This is to the nearest 10, so we're going to half that and get 5. So the safe load of the bridge is somewhere between 1495 and 1505. This is to the nearest 1, so it's a half that we need to add and subtract. That means the weight of the soldier is somewhere between 75.5 and 74.5. What's the maximum number of soldiers that can safely cross the bridge? So this is a division. We want to do the load of the bridge divided by the weight of the soldiers that are actually crossing it. Now if we want that word safely in here, we're actually looking for the lower bound. We want to say no matter how accurately we've done these soldiers, these guys will definitely get across. So if we want a lower bound for a division, we want to do the lowest value of the load divided by the highest value of the weight. And that's going to be 1495 for our load, 75.5 for our weight. And that would give us 19.8, but we can't force 0.8 of a soldier to walk, so we have to round that down and say that 19 is the safest, is the maximum number of soldiers that could safely cross the bridge. We could get an upper bound and get a value higher than that, but that wouldn't be safe. So it's a weird sort of double cloaked question, that one. For our second question, we've got a distance of 310 miles correct to 2 significant figures. The second significant figure is in the 10s, so this is to the nearest 10. So our distance is somewhere between 315 and 305. Petrol to the nearest litre, so that's the nearest 1. So 1 divided by 2 is 0.5. And the amount of petrol is somewhere between 50.5 and 49.5. Miles per litre, the maximum value for the petrol consumption. So we want miles per litre, that is a division. That is M divided by L, or what are we using? That is D divided by P. We want the maximum value of this, so we are going to do biggest value of D divided by smallest value of P. And that means we're going to have to do 315 divided by 49.5. That would give us 6.36, yeah, something like that. And what we're talking, that is miles per litre. You can have, obviously, a decimal for that sort of sum, so we don't need to round it. Okay, once again, I'd like you to have a go first. Pause the video. I'm assuming you're unpausing now. Our crane has this strain of 5,300 to 2 significant figures. The second significant figure is the 3, which is in the hundreds column, so we've rounded to the nearest 100. So that means that we can put 50 on either end. This is between 5,250 and 5,350. The crates weigh 100 to the nearest 10, so if we halve that, that'll give us 5. So the crates are between 95, let's call this strain then. This is between 95 and 105. What's the greatest number of crates can be lifted so the cable does not break? There's two ways of reading this question. I'm going to choose to read it in terms of safely, and if I want to do it in safely, I want to find the lower bound. But I can see that you could read this and say, well, let's try and push this as far as we can. Let's go for the upper bound. I've got a feeling the question will be a little bit more precise, but we're going to find a lower bound. If we want to do that, we want to do the strain divided by the crate sort of height, because we want to see how many crates fit in that, crate weight, sorry. So if we want to find a lower bound for a division, we want to do the lowest value of the strain divided by the highest value of the crate. So that's going to be 5 to 50 divided by 105. And that's going to give us, rather unusually, exactly 50 crates. Now, just for the sake of comparison, if we were going to find the upper bound, we'd want to do the upper bound for the strain divided by the lower bound for the crates. So we'd be doing 5,350 divided by 95, which would give us 56.3, so 56 crates would be the greatest number that could possibly be loaded on there. I still think it's the 50 that they're after though. Now for the last one, we've got a book and a front cover and 100 pages. The front and the back are 0.8 millimeters thick to 1 decimal place, so let's do them first. So the covers, rounded to 1 decimal place, that's to the nearest 0.1, so we're adding and subtracting 0.05 from our values. That means our covers are between 0.75 and, let's call that C, and 0.85 millimeters thick. The pages are 0.15 to 2 decimal places, so 2 decimal places means we're going to the nearest 0.01. If we halve that, we'll get 0.005, and so the pages, let's call them P, are between 0.155 and 0.145. We want to calculate the minimum thickness of the book. That is very definitely a lower bound for how thick the book is. There are 100 pages, there are 2 covers, so we'd want to multiply this by 2, multiply this by 100, and then add them together. So if we want to find the lower bound for a multiplication, let's look, we're looking for lower bounds of everything. So we're going to do 2 times 0.75, 2 times our lower bound for the covers, 100 times 0.145, and we're going to add those together. That would give us 1.5 there, and that would give us 14.5 here. Put them all together and we're going to get ourselves to 16 millimeters as the minimum thickness of that book. There you go, bounds. Best of luck.